When people hear quantum computer, they often imagine a magical black box that instantly solves impossible problems. But the reality is much more interesting. And building one is less like writing software and more like constructing a delicate physics experiment.
Exactly. A quantum computer isn't just a faster laptop, it's a different kind of machine built around the laws of quantum mechanics. So the hardware, the environment, and even the way we think about computation itself changes.
Yeah, and let's start, of course, at the natural place to start, which is the fundamental unit that we use in quantum computers. It's called the qubit. So it's basically like they took the bits, the ones and zeros, and the bytes that we use in normal computers, and they just added
Yeah.
a QU before that, and they just said it's a qubit. That's a quantum bit, basically. Okay.
If only it were that
And
easy.
yeah, if only it was just QU before the bit. It's a bit more complicated than that, which we'll come to. So in classical computing, that's what it is. Bits, zeros and ones. And a qubit, it can exist in a superposition of both states at once, is the so-called general overview of it. And we might get into a more exact view of it later on.
Yeah,
But yeah,
yeah.
that's the gist of it.
Yeah, that's what essentially gives quantum computers their theoretical power. When several of these so-called qubits interact with each other, they can represent
Yeah.
many possible states simultaneously instead of just one state at a time. And the difficult part is making that happen in real physical hardware without the whole system or the quantum state actually collapsing.
Right, because a qubit, it's not just an equation in a physics paper. It has to like physically exist in the real world somewhere. Like it may be inside an atom, in a circuit, or a beam of light. And different research groups around the world are building qubits in very different ways. It's just a term that can be abstracted to many different analogies or different possibilities that different researchers are perceiving or using different perspectives to use, like to analyze and make a quantum computer using that, basically.
Yeah, yeah, that's right. Some researchers are using superconducting circuits, others are trapping ions, some are manipulating photons, and some are arranging neutral atoms in laser arrays. I know it sounds all very physics
Very
like
sci-fi.
heavy. Yeah, very sci-fi, very physics heavy, but yeah, that is precisely what all of these people are doing. What you need to know is that the same principle of quantum mechanics lies underneath all of this stuff, but the physics looks completely different depending on the platform that you use, if that makes sense.
Yeah, it's just different domains of physics and different like approaches to get the same idea of a qubit, to
Yes,
get the same
yes,
idea of a quantum computer that can be more efficient than classical computers, essentially, right?
yes.
So let's start with the approach that's probably the most developed one today, which are superconducting qubits. Basically, companies like IBM, oh, it's a really small company, and Google, it's an even smaller
Sure.
company. Yeah, like the world's smallest companies. Like no one has heard of IBM and Google, but these companies fabricate tiny electrical circuits onto chips that behave like quantum computers. Like they behave quantum mechanically, basically.
Yeah. When certain materials like weird rare materials are cooled very close to absolute zero, which is around minus 273 degrees Celsius. By the way, colder than outer space even. Yeah, when these
Zero.
materials are cooled to that temperature, they become what we call as superconductors. So electrical current flows through them without any sort of resistance, and the circuit begins to exhibit some discrete quantum energy levels instead of just behaving like a regular circuit that you see in your everyday life.
And in that like setup, a key component is something called a Josephson's junction. It's basically two superconductors separated by an extremely thin insulating barrier. And
Quantum
quantum
tunneling,
tunneling,
yeah, yeah.
like
Oh,
lets current pass through that barrier,
yeah.
essentially.
Yeah. And
Yeah.
this basically creates energy states that can represent the zero and the one of the qubit. By sending very carefully timed microwave pulses, like, yes, the waves in your actual microwave, those are microwaves as well. So by sending waves like those, researchers can rotate those states and then they can create so-called superpositions.
Right. And one advantage of this approach is manufacturing. These circuits that we just spoke about, they can be fabricated using techniques similar to semiconductor chips. So like TSMC is making
Yeah.
normal computer chips, they can probably make chips like these quantum chips as well. So you can paste dozens or hundreds of qubits on a single processor using this technology.
Yeah, and the trade-off you have here is all about stability. So superconducting qubits lose coherence fairly very quickly, usually in microseconds or milliseconds. So the operations that they perform have to be extremely fast.
And this is a very different philosophy or a method compared to the different philosophy of trapped ion quantum computing, where you, instead of building artificial atoms out of circuits, researchers just use actual atoms
Yeah, actual atoms that we all know, like how we
that
use
physically exist.
silicon and phosphorus in our everyday devices, basically atoms like those. So they are charged atoms or ions, and they are suspended in space using electromagnetic fields inside a vacuum chamber. Basically, sci-fi stuff that goes on in CERN, something similar to that, but they are not accelerated to the speed of light. That's it. They are just
So
suspended.
almost the speed of light.
Yeah, sorry. That's my bad.
Yeah.
Almost the speed of light. But they are just suspended in like a chamber like that. So lasers cool those charged ions until they can barely move, and their internal energy levels act as the qubits that we want to use. Yeah.
And since temperature is literally the measure of average kinetic energy, and that's why you said that lasers cool them until they barely move. That's how the relation between cooling and barely moves
Yes.
comes in,
Yes.
because they're no longer moving, and that's what temperature is essentially, right? And as you said, that internal energy level that acts as a qubit, and those energy levels are incredibly precise. So that basically means that trapped ion qubits, they often have very long coherence. So very long doesn't mean like a few hundred years or anything. Like compared to the previous case, which was I think a few milliseconds, in this case they can remain stable for a few seconds, which is 10 raised to 6 times, which is a million times as long as the previous method, which is a huge upgrade. But yeah, it's still a few seconds, but it's a million times better. Let's just say that.
Yeah. I mean, it is an upgrade, but scaling at this level just becomes a little bit more difficult because when you get to controlling a few ions, that is manageable, right? But controlling thousands of them interacting together at the same time is an engineering challenge which is on another level. That's just it.
That's true. And basically, as the number of ions that we use in the system, as you said, as they get to thousands, then there's like it's kind of like the n body problem, where the more bodies you introduce, the harder the problem gets.
Yeah.
Except I think the n body problem was proved to be unsolvable. This is definitely not. This hasn't been proven yet to be unsolvable, and people are like companies are working on it, and I'm pretty sure it is solvable. But yeah, it just gets way worse as you increase the number of involved qubits or the ions, right? So another approach that researchers are using is photons, which are again the particles of light. And in these systems, the qubit might be encoded in a photon's polarization or its phase. So it's like basically the relative difference between two wavelengths of light, like that's the phase difference. And that's what they use to encode the qubit in, like the polarization or the phase of the.
Yeah. Photons are very, very good carriers of quantum information because they interact very weakly with their external environment. And that means that they can travel very long distances without losing their quantum state. Just think about it. The photons that we get from the sun don't lose their states, even though they travel, I don't know, how many millions of miles from the sun to the earth. So that's how
Yeah.
powerful photons would be in this case. Just imagine.
Yeah, they travel for 8 minutes at the speed of light. So that's a long distance. So that is precisely why photons are especially promising for quantum communication, because people sometimes talk about a future quantum internet that is literally built from these systems that use photons for encoding information.
The only difficulty about this part is that photons also barely interact with each other as well. So quantum algorithms often require entangling qubits, and photons would just prefer to fly past each other and mind their own business rather than having anything to do with the other photon whatsoever.
And coming back to the sun and the earth, it's a distance of 93 million miles, is as far as I get,
Damn.
I think. So yeah, it's a long distance. Then, like, moving on for another, like, to get to another method, neutral atoms. So this is a rapidly developing approach where researchers trap ordinary atoms using tightly focused lasers that act like microscopic tweezers, essentially.
Those atoms can be arranged into very large arrays, sometimes even hundreds at a time, and they form something like a programmable lattice. So the lattice structure that you may have heard of when you were studying physics
Yeah.
or chemistry in ninth or
Yeah.
10th grade. Yes, it's that same lattice, a very structured, very predictable form in which those atoms are arranged. And lasers then excite these atoms into very high energy states called Rydberg states.
And like then that links to like lattice enthalpy and stuff like that, which you might have also learned of in your classes. So based on what you just said, those Rydberg states, in those states, the atoms interact strongly with their neighbors, and that allows researchers to create entanglement between qubits. Basically, we've spoken about this earlier. It's literally quantum entanglement. So you're literally affecting one atom or one qubit from the spin or the position, or like mainly the spin of another qubit, right? So essentially, that is a clever trick that turns ordinary atoms into a controllable quantum system. So it's a
Okay.
huge thing.
Yeah, so the field now has several competing architectures, I would say.
Yep,
Superconducting circuits
definitely.
are fast and they're scalable on chips. Trapped ions are extremely precise, but not too good at scaling. Photonic systems excel at communication, and neutral atoms scale well onto large arrays. That's
Yeah.
what I get.
Yes, you've summarized it up very well. So
Yeah.
the interesting thing is that all of these different methods or approaches, they're all like they all have their own pros and cons. Thing is, no one really knows which one will dominate at the end, or maybe
Yeah.
it's going to be a combination of them, or maybe it's going to be, who knows, maybe none of these are good enough, and there'll be like a different way of making a quantum computer. Who knows? The industry is still like in the early phase where multiple technologies are racing forward at once, and there's only time will tell which one's the best one.
Maybe we can think of it a bit like the early days of aviation, right? At one point, people were experimenting with spy planes, gliders, different types of stuff, basically. Lots of strange ideas before the modern airplane design eventually emerged out of all of this nonsense. So maybe it is similar to that, and maybe um, you know, 15, 20 years ahead, we will find and lock into that one design or architecture that we will use going forward.
I mean, everything requires trial and error. You can't reach the perfect
Yeah, of
architecture or
course.
the perfect airplane in the start, right? So that's fine. So, regardless of the architecture, all quantum computers face the same fundamental challenge, that quantum states are incredibly fragile. Again, it's on the order of like a few milliseconds and sometimes a few seconds as of now. So any interaction with the surrounding environment just destroys them, and then it renders them useless. So that's a really important so-called pain point that affects all of the approaches that we mentioned above.
And for superconducting systems, that means operating at temperatures that are colder than outer space, like I had mentioned before. Quantum chips still sit inside dilution refrigerators, which are cooled to around 10 millikelvin. So basically, as close to absolute zero as you can get.
Yes, like it's really, really, really close. Yeah. And that 10 millikelvin is around 100 times colder than the natural temperature of deep space. So if your coffee were that cold, you'd have bigger problems than caffeine withdrawal. You'd just like, it'd just be, let's just say it'd be bad. Let's not talk about that a bit more, because cold coffee would have a whole nother meaning on if it were 10 millikelvin.
I mean, sure, but getting back to the point, inside this whole refrigerator sits a very, very small quantum chip that is only like a few centimeter across in width. But it's connected to like maybe hundreds of layers of control electronics that send those microwave pulses down carefully through engineered wiring.
and those pulses. And by the way, this is all in like, because it's in like such a cold environment. This is essentially the field of quantum cryogenics, and how people try to keep it stable at that temperature, and how they manage to reach that temperature in the first place, because it's just really difficult to do that in the first place. But yeah, so point is, those pulses that you spoke about, those pulses manipulate the qubits, they create superpositions, they perform quantum gates, and they entangle multiple qubits together, as we spoke about earlier. It's kind of like programming the processor to you, and it's using precisely timed bursts of electromagnetic radiation, like those pulses, to do those different things like entanglement, performing quantum gates, and creating superpositions.
Yes, entanglement is the key ingredient over here. It links qubits together so that their states become correlated in ways that classical systems just can't reproduce.
And the issue here, again, the con of the so-called hardship that all of these approaches face. Yeah, it's basically that creating reliable entanglement is extremely difficult, because, as we said earlier, any small disturbance or even tiny electromagnetic disturbances, they can introduce a lot of errors, and those errors can compound, and it's kind of like compound interest. Those errors are just going to keep getting worse the more qubits you have, and if each qubit has an error, it's just going to be bad. Simple as that. Like, that's it.
That's why researchers care so much about error rates rather than just qubit counts. A machine with more qubits isn't necessarily better if those qubits are extremely noisy and the error rate is bad. So you
Right.
would like to have a machine which has an optimal amount of qubits but a very, very low error rate. And that would be much better than any other machine as well.
Right, yeah. The whole idea is to balance it out and maximize the number of qubits while minimizing the error rates. So that's the real goal, right? Stable
Yeah.
and those qubits have to be stable with really long coherence times. And the ideal scenario is a zero error rate, which I guess is not going to happen anytime soon. But like low error rates are, I guess, good enough, right? And
Yeah.
that leads to one of the hardest challenges in the field, which is quantum error correction. Basically, how do you correct those errors and how do you reduce those error rates?
For classical computers, it's very easy. Like it's almost built into the system for them. But for quantum computers, they have a tougher job cut out for them because measuring a qubit can sometimes destroy the information that is stored in it as well. That's
Right.
kind of a trade-off that you have to make when you are designing this sort of a system.
Right. And to sort of as a workaround to this, researchers encode one logical qubit across many physical qubits. So the system can detect errors indirectly without collapsing the quantum state. They kind of link it together in advance so that they can measure. They don't, like, again, as you said, so that they don't destroy the information stored in the other qubits, and they save it and they can detect the errors indirectly without collapsing the quantum state, as I said.
That's extremely good, but the only downside is overhead over here. Sometimes estimates suggest that you might even need hundreds or even thousands of physical qubits just to produce one single reliable logical qubit. And
Yeah,
I
that's a
think
really bad ratio.
right now we've only reached to the point where we have like I think in the maximum amount of qubits we have in quantum computers is just like hundreds of qubits. So yeah, it's a pain.
Yeah, and while the ratio can range from 10 to 1 to 10,000 to 1 for those qubits, the range in terms of quality and the noise and the error correction still varies widely. And let's say we have even a 10,000 is to 1 or a 10 is to 1 ratio. With a better ratio, you still might not have the number of qubits required, because, like, today's quantum computers, which have machines with like dozens or hundreds of qubits, they're still experimental platforms. They still don't. Basically, you have to again pick between the trade-off of having number of qubits versus the lower error rates. Like, for example, there's this company called Quantinuum, which has 50 qubits, but with very low error rates. So they're all reliable qubits. And you can get into the ratio of qubits of logical qubits and physical qubits on their website. Like, there's a lot that they're doing.
I mean, despite all of this stuff as well, all machines are incredibly useful for research, even those that have a dozen ranging to even hundreds, right? Because
Yeah.
scientists can still test their algorithms and simulate small quantum systems and explore new, maybe computational ideas that they have on these machines and get feedback on both systems as well. So on their ideas and on the machine as well.
Right. Like testing is really important. And the whole idea is to use and people are using quantum computers to make quantum computers better. That's literally a self-recurring process. So one area people talk a lot about is chemistry and material science. Because quantum computers naturally simulate quantum systems, they could eventually help develop new drugs or better battery chemicals. And this is like, let's just say this has gone around the internet like a lot. It's like been widely circulated that our quantum computers are going to help us find new drugs. It's going to help us simulate so many of these things that were before very possible to simulate on classical computers, but they would have just taken like millions of years. So it's basically impossible at that point. So the quantum computers open this new frontier of allowing us to increase the efficiency of our simulations by a huge factor.
And here, optimization is another possibility. So industries like logistics and finance constantly solve like enormous optimization problems, and quantum computers and quantum algorithms also might offer some advantages over here.
Right, and that potential, that those possible advantages, is why corporations and governments around the world are investing heavily in the field. And the so-called like most important part of it is to know where to invest. Like these technologies are still under process, but they still work. Like it has been proven, and there are, again, as you said, quantum computers that work and are used reliably today. And at the same time, you can see that these big companies and these small companies, like big companies like IBM and Google, and smaller companies that are starting up recently, have been formed around the technology.
And at the same time, there is this whole, like you said, small companies. So there is this whole startup ecosystem that has formed around this technology. Hardware companies are building processors, software companies are developing algorithms, and there are, of course, platforms that are giving researchers access to all of these machines.
Right. You can in fact go right now to some websites online, and you can basically buy or like you can run your code, like your simulations, with a quantum computer. It's a bit expensive. I think it's, as far as I know, it ranges from like some of them are free. I've done it before for free as a test, and you can do it for like $15 a second is what I think. It's really expensive, but like that's what companies do. They run their simulations, and you can do that right now for free, like online, and you can just, because most people don't actually own the quantum computers, and that's what IBM does. It like delegates out the time that the quantum computer has, and that it's active and functional, to, and it sells it out to people that they can use, like researchers or companies or stuff like that. And they just like then researchers independently can run experiments remotely from the comfort of their own home, I guess, or like their labs, through the cloud. And they can send programs to processors located in those specialized laboratories like in IBM.
Yeah, this is just like the whole AI and cloud computing scenario that we are looking at right now. So people can't, of course, train models with PCs or laptops that they have in their homes. They need huge computational power for that. Like a lot of GPUs stacked together and different hardware components as well. So they are doing exactly what you said. Like they are leasing out those GPUs for a certain amount of time and training their models on that. And that is much better as opposed to, buying the whole system itself.
Quantum computer.
Yeah, I mean, if you really think about it, it's a bit like the early days of classical computing. Like throw back to the old times when only universities and large institutions had access to mainframes, and you had to physically go there at that time, though. You had to physically go there and just experiment with those things.
Right. And The timeline for practical quantum advantage, it's still uncertain. Some researchers think that we might see major breakthroughs within a decade. Some say it's going to be a few years. Like some companies claim that they're going to get 1 million qubits
Whoa.
in like 2 years from now, which is
Okay.
a very like
Bit of
just
a
it's a
reach.
lofty claim, lofty
It's a bit of
ambition.
a
Yeah, it's just a bit of a reach. And some people say it's in a decade, and some people say it's going to be much longer than that. Because building these systems essentially is like constant problem solving. And that constant problem solving is literally in physics, engineering, computer science, chemistry, biology, economics. Like, like you use a lot of STEM fields to solve the problems here, and that will help us solve problems in STEM fields and other fields everywhere. Like simple as that. And
so
biology is not going to be that much applicable in making it, but it's going to be very helpful in using quantum computers to like accelerate biological advancement in like every field in biology, basically.
so if the next time if someone asks you how to build a quantum computer, the answer is surprisingly complicated, right? You design qubits, you isolate them from the environment, you control them with incredible precision and fight all of these errors that pop up constantly.
I mean, I'm not surprised that it's complicated. It's a quantum computer. It's not rocket science, but I think it might be harder than rocket science. Uh,
Yeah,
rocket
yeah, I
science is a
agree.
done
I
deal at
agree.
this point.
I
Because
agree.
rocket science, yeah, exactly. Rocket science has been done before being
Proven. It's
made.
proven. It's scalable to the point
Reliable.
where yeah, it's reliable as well, and it's better scalable than quantum computing because we can actually somewhat predict the outcomes of rocket science, but nobody still knows what to do with quantum computers ahead.
Because rocket science clearly follows the laws of physics, and quantum computers are meant to follow the laws of physics, and we are constantly developing new laws of physics for quantum states. So that's
That
an
that is
active
that is the only
process.
problem.
Yeah, that's the only problem, that we don't know what's happening.
Yeah,
Um,
we are still
simply,
early in that journey, right? I mean,
yeah.
today's machines are closer to scientific instruments than everyday computers. But as we all know, history shows that when a new computing paradigm appears, it eventually reshapes entire industries.
Right.
So,
And a quick side point that I just wanted to note is you can think of, so there are classical computers, there are supercomputers, and then there are quantum computers. One analogy that I would like to give that I heard from like a person at a quantum computing company, you can think of a supercomputer as a horse-drawn carriage, a
okay,
classical computer as a just like a person walking, and a quantum computer as a fighter jet.
okay,
And the relative speeds of those is what you can compare,
I see
and
your
that is
point.
how much faster a quantum computer is than the other two. The supercomputer is way closer to a classical computer than a quantum computer is to a supercomputer. It's a huge difference. So yeah. So anyway, back to the point. So if we are building a quantum computer, we have to also build an entire ecosystem around them. Algorithms, software tools, real world applications. And we're still early in that journey because today's machines, as you said, they're like, they're not that good, like they're good, but the classical computers and the supercomputers yet. They're still, they can't do quantum entanglement. They can't do quantum
Mm,
superposition.
yeah,
They're still like baby level right now. That's
yeah. I mean, but I guess that's what makes this field so fascinating, right? It's no longer just theory. It's a global engineering effort to build the computers of the future. And
right.
yeah, next time maybe
And
we can explore what kinds of problems these machines could realistically solve.
I mean, that's true because building the hardware, as complicated as it seems right now, might
Yeah.
actually be the easy part. But the thing is that these machines that are being built today, they just might be the very first prototypes. Who knows what's going to come next?